Good day. So, today we will talk about multiple access. Okay. Now, what is multiple access? If you remember that we had 7 layers in the so called OSI stack, the top one being application, then we have presentation, session, transport, network, link and physical. Okay. We had been mostly talking about the physical layer till now, although for optical networks we sort of ventured into some of the higher layers. But from this lecture onwards we want to concentrate on the link layer. Okay. Now, what medium access does is it coordinates competing requests. Requests for what? For medium. That means that there is a medium which may be an object of contention, meaning that I mean several nodes may want to use it, and this medium access control protocol has to do with how to handle that. So, sharing of link and transport of data over the link, that is in general the description of what the data link layer does. So, when we share a link, there is a question of competing requests and we have to have some way of resolving that, and of course, there is also a question of transport of data over a link. A link, if you remember, when we say a link, I mean that two nodes which are connected, the nodes may be computers or routers, switches, etc., the two networking nodes, they are directly connected. Now, when I do like this, it might mean a cable, a copper cable or a fiber, or it might mean a shared medium like the free space. Okay. So, there is but there is some way of communicating directly between these two nodes, that is what we mean by link. That means that is just one hop in the network, that is what we are talking about in the data link layer. So, there is a question of reliable transfer of data over this link, and if this link, like when you have a free space transmission with so many nodes in the network, now so many people would like to transmit. So, there is a question of sharing this medium, and there is a question of who would access it when, and just as a free space could be a shared medium, similarly if you remember that if you have some kind of a bus, if you remember our discussion about topology of networks, when we have some kind of a bus from which a number of nodes are hanging, and that bus may also be an object of contention. So, that bus is the medium through which communication is taking place, and there is an there is some kind of competition or sharing between the of this medium between the nodes. So, we have to handle that, that is the other thing. So, actually this link layer may be divided into two sub layers, so to say. The upper one is the logical link control and the lower one is the medium access control. So, we will talk about logical link control later. So, we start about with medium access control. There are a number of medium access control protocols and techniques. So, we will discuss a number of them. So, the situation we have is computers in a shared network environment, and although the medium is shared, it is taken that only one computer can transmit at a time. If two computers try to use the same line at the same time for transmission, that is, I mean of course, when one is transmitting, one or more may receive. For receiving is not a problem, but when two computers want to transmit at the same time, their messages get garbled. So, we say that there is a collision. Okay. Now, how can we organize the transmission so that all computers are given an opportunity to exchange messages? Okay. If you remember that when we were talking about multiplexing, that is also in some sense we are sharing a medium. Okay. So, we had this time division multiplexing and frequency division multiplexing. Actually, we also have time division multiple access and frequency division multiple access, etc. over here. The difference between the two cases is that in the multiplexing case, they are all at least the lines are all coming together into the multiplexer, all right, whereas when we are at least in most of the cases, whereas in multiple access the points are all distributed, so geographically distributed, So, they may not know about each other, there may or may not be much of a coordination. In some schemes we do have some coordination, in some schemes we do not have any coordination. So, all these cases we will see. There may of course be point to point links in a network like PPP for dial-up access etc., which is quite common. Point to point link between Ethernet switch and a computer. So, these are examples of point to point link, we will come to this later on. And then there are broadcast like a traditional Ethernet where a cable was shared. Upstream in an HFC, HFC is hybrid fiber coaxial. So, some part of it is fiber, some part of it is coaxial, and the upstream traffic there that also uses that medium as a shared medium. Then we have that 802.11 which is a wireless standard. We will have a separate lecture on this wireless networking etc. So, 802.11 is the number of the standard which defines some form of wireless networking. So, wireless of course, it is a shared medium because it is sharing this our common shared electromagnetic field that we all live in. So, there may be a single shared broadcast channels, there may be many also or more than one also. Two or more simultaneous transmission by nodes will mean interference. So, only one node can send successfully at a time. Multiple access protocol is a distributed algorithm. So, this is where it differs from multiplexing. It is a distributed algorithm that determines how nodes share channel, that is determine when node can transmit. Communication about channel sharing must use the channel itself. Okay. So, that means we have what we earlier called in-band control, that means usually that means if you are let us say a wireless network, if you are running any kind of protocol for control purpose etc., that is also going to be using the same medium. So, the same question of how to coordinate that with all the other competing nodes which are trying to transmit data, all that comes into play. There are centralized approaches to a MAC, that is the medium access control, and the centralized approach is in some sense it may be simpler, in the sense that there is a controller which grants access to medium. It is simple, greater control, priorities, quality of service etc., all these can be implemented very easily. For example, if you want to give higher priority to one particular node, the controller simply just takes note of the priority when allocating the medium to a particular node. But there are problems with centralized approach also. One is that a single point of failure that is of course a big problem, because if you whenever you have a centralized system and if that system fails, that central system fails, then the whole network is down, which is not a good idea or which may not be a good idea in many situations. Okay, that is one thing. And secondly, there will be performance bottleneck, meaning that first of all that central command, I mean everybody is communicating to it, but when the network becomes bigger, so the demand on its computational capacity, its control mechanism etc., that goes up very proportionately. So, that is also another problem in centralized approaches. And in decentralized schemes, all stations collectively run MAC to decide when to transmit. So, in a decentralized scheme we are running some kind of a distributed algorithm. There are various kinds of MAC protocols. One is called something like a round robin MAC. Round robin, you know that there are a number of stations and each station takes its turn in a round robin fashion. Alright. So, that is a round robin MAC. There are some protocols based on round robin MAC. So, here each station is allowed to transmit, station may decline or transmit, that means it may have nothing to transmit, in that case it may decline, otherwise it will transmit. It could be centralized, for example polling, or distributed, for example token ring control. So, the control may be centralized or distributed of who is next to transmit. When done, station relinquishes and right to transmit goes to the next station. This is efficient when many stations have data to transmit over extended period. So, that may be a good scheme. There are scheduled access MACs, like time is divided into slots, just like our time division multiplexing. Station reserves slots in the future, multiple slots for extended transmissions and suited to stream traffic. There is a question of reservation of some slots. Okay. So, that would be a part of the protocol, that how reservation will be done, who can reserve, and if two people want to reserve simultaneously, then what happens. So, you have to handle issues like that. So, this is a scheduled access MAC, when it is a schedule is sort of, or some reservation is done beforehand. Then there are some contention based MAC. Contention means there is hardly any control, there is no control. Okay. Stations simply try to grab the medium, this is distributed in nature. Surprisingly, I mean, for no control it performs quite well for bursty traffic, but it can get very inefficient under heavy load. Okay. Actually, the round robin MAC that I mentioned before and the contention based MAC, these are very common. Contention based MAC is of course the most common example is the Ethernet, which we will see specially later on how it is done, or satellite communication. These use contention based MAC, that means nodes simply go and try to grab the control, but if the load, that means the over a long period of time, I mean very roughly I am talking that over a long period of time, how much data, I mean how many times the nodes on an average try to communicate and for how long, that means what is the transmission time. So, these two factors together define the load on the system, and if the load is light, then these contention based protocols quite very surprisingly well, and of course, they are much simpler and maybe cheaper to implement. So, examples of contention based are Aloha and slotted Aloha. These refers to some protocols which are used in satellite communication. So, we will discuss these when we talk about satellite communication. We have CSMA, it stands for Carrier Sense Multiple Access, or CSMA CD, which is Carrier Sense Multiple Access with collision detection. There are other variants of these like Carrier Sense Multiple Access with collision avoidance and things like that. So, these Aloha, slotted Aloha are for satellite. CSMA, CSMA CD or specifically CSMA CD is used by Ethernet in many situations, and then we have our CSMA CA maybe for cellular communication, etc. So, these are contention based MAC. And round robin, these are token based protocols, and so two very common ones are token bus and token ring. So, actually we will discuss these in the next in this lecture as well as the next, we will be discussing these. So, I mean we can sort of summarize. First of all, we can divide the networks into two types depending on their topologies. One is a bus type, that means bus means some communication channel and everybody is connected to the same communication channel. It may be a coaxial cable or some fibers, or it could be a ring, all right. And then we have this token bus, which is one particular MAC protocol. It has got the IEEE standard number 802.4 or polling in 802.11, we will come to this later on. So, these are examples of bus type topologies using round robin techniques. Token ring is a ring type topology, 802.5 is the standard number, or FDDI, these are round robin, but the topology is a ring. There are scheduled approaches to medium access like DQDB, so distributed queue dual bus 802.6. So, we will be talking about this also. Contention based CSMA CD, CSMA CA in 802.3 and 802.11. So, first one is Ethernet and the second one is wireless networks. So, we will look at these in later lectures. So, what is the ideal of a multiple access protocol? Suppose we have a broadcast channel of rate Rbps. Any broadcast channel would have some maximum limit or to the rate at which you can send some or you can communicate over it. That depends on the characteristics of the medium. For example, so if the medium is different, this rate R may be different. For example, the rate for a fiber optic cable would be much higher than the rate for a coaxial cable, let us say. But the point is that there is always an upper limit due to various reasons. We need not go into that in this lecture due to various reasons of how we communicate, etc. So, there is a maximum rate R which you can achieve on a particular medium using, let us say, the technology which is present. Now, when one node wants to transmit, it can send at rate R, there is no problem, it can send all the way up to rate R if the technology permits. When m nodes want to transmit, this R is not going to change. So, what you want to do is that you want to divide up this rate R and distribute it amongst these m nodes which want to communicate. So, each can send at an average rate R by m. If that happens, naturally we have a very ideal multiple access protocol, we cannot do better than that. But of course, it is difficult to achieve this theoretical rate, because there will be some overhead for the protocol itself which will eat up something, and then none of the protocols are 100% efficient. Secondly, it is we would like it to be fully decentralized. Okay. So, no special node to coordinate transmissions, no synchronization of clocks and slots, and lastly it will be simple. So, naturally if it is decentralized, no synchronization, etc., that is one aspect of simplicity, then the protocol itself should be simple. So, this is the other thing, and of course, we want a fully decentralized scheme. I mean, we prefer them because there would be no failure of single nodes, etc., and then there is no bottleneck. So, these problems would be avoided if we have a fully distributed system. Now, we have in multiple access, as I mentioned, many users sharing a resource at the same time needed, because users must share the cells. First, let us talk about three different multiple access: frequency division multiple access, time division multiple access, and code division multiple access. Okay. Frequency division multiple access and time division multiple access are very simple, should be simple, because we have already talked about multiplexing. Only thing is that there is slightly, the connotation is slightly changed over here. Code division multiple access is somewhat different, so we will discuss it in some more detail. So, use the same frequency, same time, and but different codes, we will come to that. So, let us start with FDMA. FDMA is frequency division multiple access. Just like frequency division multiplexing, channel spectrum is divided into frequency band. Each station assigned fixed frequency band. Unused transmission time in frequency bands go idle. So, this is the simplest possible scheme. Okay. It is also not very efficient, of course, because many of the stations will be idle, and that frequency band for that particular time is going to, for all that time it is sitting idle, that part of the bandwidth is wasted. And also we know that in data networks the traffic is very bursty. That means people want to transmit for a very short amount of time, then for maybe suppose the transmission time is t, then maybe for 500 into t, that amount of time it just sits idle, alright. So, it is very bursty. So, a frequency division multiple access would be very inefficient, but this is the oldest, radio stations are doing some, in some sense they are doing, you can call it multiplexing, since the communication is only one way, but if you are using some other kind of, say, radio frequency transmission using fixed channels, both way communication, then it is some kind of multiple access also. So, suppose we have 6 stations, LAN 1, 3 and 4 have some packets to send. So, they are sending frequency bands 2, 5, 6 are idle. Okay. This happens quite often in FDMA. This is another picture. So, this is I mean what we have tried to show with color are the graphs of the different channels. So, the channels are differently colored these bars, and we have these three axes. One, the frequency, f is the frequency, C are the channels, and T is the time. So, there is only one channel at all times use a particular frequency, another channel at for all times use another frequency, and so on. Another frequency means, of course, there is not a single frequency, this is a frequency band kind of thing. You always require a band, you cannot communicate anything with a single frequency, that will be just a single tone. Frequency division multiple access. So, each channel gets a band or range of frequencies used in traditional radio, TV, first generation cellular, etc. Advantages is, of course, no dynamic coordination, absolutely I mean distributed. Disadvantage is inflexible and inefficient if channel load is dynamic and uneven, and this is a very great disadvantage. The inefficiency, I mean, by today's standard is quite high, but at one point of time it was quite good. We will see another version of this FDMA, which is WDMA. WDMA means that wavelength division multiple access, and as you can suspect, now we are talking about fibers. Just we have frequency division multiplexing and wavelength division multiplexing. They were actually the same things, only thing is that for fiber we choose to call it as wavelength division multiplexing. So, here also we are talking about wavelength division multiple access. Previously all our fiber links that we talked about were point to point. Okay. Now, but suppose a fiber link somehow is used for multiple access to stations in a very dynamic fashion, we want to give this bandwidth. I mean we can a number of stations can connect to the same fiber through some splitter, coupler, etc. So, we are not going into that. So, suppose somehow they are all hooked into this fiber and we want to use wavelength division multiple access. So, let us just look at the scheme. Each station is assigned two channels, a narrow channel for control and a wide channel for sending data frames. All right. So, which means that each station has two channels, a narrow channel for control and a wide channel for sending data frames. Well, the channels could also be of the same size, does not matter, but then for control we do not require so much bandwidth. Now, so for a particular node these two are assigned. A node's control channel is used by other stations to contact that node. So, its control channel is fixed. So, some other stations, if you wants to communicate with A, they will first talk to A on its control channel. Both channels are divided into n plus 1 slots which repeat endlessly. Slot 0 is especially marked to synchronize the nodes. So, each channel there are say n plus 1 slots, and then so a number of nodes, let us say 3 nodes B, C and D can communicate with A at the same time, because for communicating to A, of course, it has to send to A in the channel or the wavelength which has been assigned to A. But how can all three send at the same time? Well, if there are slots in that channel and if they have booked separate slots, in different slots their data can go. So, B, C and D can simultaneously communicate with A. So, for this to happen, each station has to have two transmitters and two receivers. First, it has to have a fixed wavelength receiver for listening to its own control channel. Its control channel is fixed, so it requires a fixed wavelength receiver. Then, if it wants to communicate to somebody else's control channel, for that it requires another transmitter, and that has to be tunable, because it may A may want to talk to B at one point of time and then talk to C at some other point of time. B and C's control channels are different. So, we sort of do it, we have to have a tunable transmitter. We have a fixed length wavelength transmitter for outputting data frames. Now, suppose it wants to talk to B, it has talked to B's control channel, then it has to have a fixed when A wants to say communicate over that over its over the wavelength assigned to it, then it can for output the data frame at a fixed wavelength. Then it requires a tunable receiver for selecting a data transmitter to listen to. A is talking to B. So, for listening to B, it requires a tunable transmitter, because it may want to listen to B now, and later on it may want to listen to C. The data channel for each station contains a special slot where the status of both the channels, which slots are free, etc., they are reported. When a station A wants to set up a connection oriented channel to station B, it tunes to B's data channel and waits for the status slot. It puts in a request in any of B's free control channel slot. B's status slot will tell him that I mean whatever control channel slots are free. So, B just puts in a request over there. When B sees the request, it assigns the slot to A and announces it to others. What happens if now this is the problem in a distributed system in the sense that you always have to worry about this kind of thing. If two stations grabs the same control slot simultaneously, both of them want to talk to B and both of them sort of wants to grab that same control slot by some chance simultaneously. Well, when we say simultaneously, they may be very close to each other. So, that will also become simultaneous. It will become garbled. So, naturally, if both of them are trying to put things in the same box, the information will get garbled and both will notice. In that case, both will back off for a random amount of time, and it is to be hoped that when they do back off for a random amount of time, the random number generated by one station and the random number generated by the other station will be different. So, both of them will back off for two different amounts of time, and whichever has had the shorter waiting time, when it comes back and tries to put again something on B's control slot, hopefully there will be no collision. So, this is one way of colliding and then sort of recognizing that oh we have a collision, so we back off. This kind of scheme is used elsewhere also, we will come to that. For two-way communication, B repeats the same algorithm for A. For variable bit rate traffic, so this is for synchronous, so one slot can be sort of reserved for this communication between A and B. Excuse me. For variable bit rate traffic, slots in the data channel is not booked. So, they can send by some other mechanism, let us not go into that at the moment. Next we come to time division multiple access. So, if you notice the figure, this looks just like time division multiplexing. Okay. Time division multiplexing. So, we have say the from the information or signal from this top one high coming and then it is sort of interspersed with the signal from this go source go, and they are sort of going in a time division multiplex fashion. Only thing to notice over here is that this line and this line, they may not be actually physical wires, that is why some wireless has been put over here. So, they are actually sharing the same medium. So, immediately you see the problem. What happens that if this nice synchronous behavior breaks down. So, somehow you have to make sure that they do not break down and they do communicate at precise slots of time which is assigned to them, and then you have the additional trouble of then ensuring that their clocks synchronize, because if he is running a clock of his own and he is running a clock of his own, these two clocks may not agree in real life. So, how to synchronize them, etc. So, these are the problems which you solve in TDMA, time division multiple access. Otherwise, the basic approach is the same as time division multiplexing. So, TDMA is time division multiple access to channel in rounds. Each station gets fixed length slots, length equal to packet transmission time in each round. Unused slots go idle. This is the simple scheme. So, example, suppose you have 6 station LAN 1, 3, 4 have packet and slots 2, 5 and 6, these are idle. So, this is a these this kind of frames sequence they keep on repeating. So, in each frame 1 will have a slot, 2 will have a slot which is going idle, 3 will have a slot, 4 will have a slot, 5 and 6 also have slots which are again going idle and so on. So, this is a TDMA system. Each channel gets entire spectrum for a certain time period, rotating time period. So, within whenever the time is allotted to that particular channel, it gets the entire spectrum to itself. So, it can send the data at a very high rate. Advantage is that it can assign more time to senders with heavier loads. So, by doing that it gains some kind of efficiency advantage over FDMA, and another side of the same coin is that you can reduce the power consumption. Disadvantage is of course that requires precise synchronization, which we talked about, which needs some doing. So, this is that diagram for the time division multiple access. The entire frequency band is given to one particular channel for a short amount of time. Then for the next short amount of time another channel gets the entire frequency band and so on. As it is there in standard time division multiplexing, the same thing applies. Now, we can combine TDMA and FDMA. Each channel gets a certain frequency band for a certain amount of time. Example is GSM, we will come to this maybe in slightly more detail later on. So, this is combining both TDMA and FDMA, that means we are breaking it up not only in the time domain, but also in the frequency domain. Advantages is that more robust against frequency selective interference, because for a particular communication the frequency is sort of changing. Much greater capacity with time compression, inherent tapping protection. So, it has got a lot of advantage, and of course, it is quite efficient. Disadvantage is of course once again just as in TDMA that we have to synchronize the clocks etc. So, here frequency changes must also be coordinated. So, this is a picture. So, basically we have small blocks. So, for this particular, let us say this yellow block over here. So, for this particular time, at this particular time, for this particular frequency range is given to this channel and so on. Okay. Next we come to channel partitioning or CDMA. CDMA is code division multiple access. So, this may be something a little interesting and new. Excuse me. So, we have an unique code assigned to each user, that is code set partitioning. Code, what is that code? We will come to that. Used mostly in wireless broadcast channels. So, like cellular, satellite etc. All users share same frequency, but each user has its own chipping sequence, that is code to encode data. We will come to details. So, encoded signal is original data and then there is some operation with the chipping sequence. So, we will come to what is chipping sequence, and decoding is inner product of encoded signal and chipping sequence. Allows multiple users to coexist and transmit simultaneously with minimal interference if codes are really orthogonal. So, what do we have? A number of stations share a number of channels. Each station transmit over the entire spectrum all the time, okay, which means that it is not excluded either in the time dimension or in the frequency dimension. Each channel can go on communicating in the entire frequency band all the time. Now, how will that happen? Because other people are also communicating in the entire frequency band all the time. So, their all their signals will get mixed up. As a matter of fact, they do get mixed up, but the point is that the signals are encoded in such a clever fashion that from that mixed signal you can separate out all the different streams of communication that have gone into it. All right. So, multiple simultaneous transmissions are separated using coding theory. Assumption, of course, there is an assumption that signals add linearly. If it does not, then you have to do some adjustment etc. We will not go into that. So, this is some kind of also known as spread spectrum system. This is one kind of spread spectrum system. So, CDMA is a form of spread spectrum multiple access. it is spread over the entire spectrum. Instead of sending b bits per second, for a particular node wants to send b bits per second, we send mb chips per second. Now, what is a chip? That means each bit is encoded by m number of chips. So, chips are sort of tiny fragments of bits, you might say, and these chips may again be 0 and 1. So, there is a 0 1 sequence code for the bits of one particular station. Another station will have another code. A 1 megahertz channel with 100 stations give 10 kilohertz per station. With fewer than 100 chips per bit, the effective bandwidth is higher and the channel allocation is also done at the same time. We will see how. So, this is the picture, which is a funny picture, because for the entire time, for the entire frequency band, all the channels are using it at the same time. Now, each channel has unique code, as I mentioned. All channels use same spectrum at same time, but orthogonal codes. It is bandwidth efficient, its capacity is also quite good. I say of TDMA when I talk about simple TDMA, okay, but you can sort of mix up FDMA, TDMA and get a good efficiency over there also. So, this fight between GSM and CDMA, this is quite ongoing and it will go on for some time. Disadvantage is that it is more complex signal regeneration. So, this is how it is implemented. As I said, each bit time is subdivided into short intervals called chips, and typically there are 64 to 128 bit chips per bit. That means, for each bit we have a code which is 64 chips long, or I mean if chips this word sounds a bit unfamiliar to you, that means each code is 64 bit long. When I say bit, actually you think it as that each bit is actually encoded using 64 chips. Chips are again ones and zeros, sequence of ones and zeros, all right, 164 or 128. So, we are sending a long sequence of ones and zeros for sending maybe 1 1, all right, but we are sending it very fast, and we can send it very fast because we are using the entire spectrum. So, the entire spectrum is at our disposal, so we can send very fast. So, each station is assigned a unique m bit code or chip sequence which is used by the station to transmit a 1, its complement is used for 0. We will see an example, but so this is just this thing. Two codes S and T are said to be orthogonal. We have been talking about orthogonal codes. If under a certain operation, and we are going to define this operation, we have S, let me call it a dot for a dot product kind of thing at the for the moment. So, S dot T is equal to 0 and S dot S equal to 1. You see that this is very similar to dot products in vector. If you have two orthogonal vectors, their dot product is going to be 0, whereas the same vector when it's when you take its dot product with itself, it is going to give you some value. We are representing it as a 1, all right. So, we define the following. Now, let us define this dot operation for our case. So, S dot T is equal to 1 by m into summation of Si Ti I is equal to 1 to m, and this will be equal to 0 if and only if S is not equal to T. We will see this. If 1 and 0 are represented by plus 1 and minus 1 respectively, we find that S dot S equal to 1. This is very simple, because if the ones have been represented as 1 and 0 has been represented as minus 1, so S dot S, so minus 1 will get multiplied with minus 1 giving you plus 1 and 1 will also give you 1. So, all of them would be 1. So, all m of them would be 1. The sum total in the previous, if you look at the previous sum definition, the sum this sum Si is going to be sigma Si is going to be m. You divide that with m, so that will give you a 1. Okay. So, S dot S would be 1, whereas for any other code, any other T where the T is orthogonal to S, this sum is going to come out as 0. That is how we cleverly assign the codes. Consider a code T where the number of chips of T which are the same as those in S is the same as the number of chips of T which are different. Okay. So, just consider what it is saying, at code T where the number of chips of T which are the same as those in S is the same as the number of chips of T which are different. So, the number of chips of T which are the same as those in S. So, the corresponding chips when multiplied together will give you so many ones. Okay. Now, if it is the same as the number of chips of T which are different, now the chips if they are different in T and S, when the corresponding chips are multiplied they would give you minus 1. Okay. Now, so many minus 1, and the number of plus ones and the number of minus ones, if they are the same, when you add them together in the previous summation, the sum total will become 0. Here S dot T will be 0. Note that S dot not of T, not of T is just the complement of T, that means the ones and zeros, well actually ones and zeros you remember are represented as with ones and minus 1. So, ones and minus ones are flipped in one of them. So, naturally the number of chips which are different becomes the number of chips which are the same, and the number of chips which were same earlier, the chip positions which were same earlier now become different, but anyway their numbers are equal. So, once again we have S dot not of T is 0 and S dot not of S. What is that? Well, all the ones in S will be minus 1 in not S, and all the minus ones in S would be 1 in not S. So, the in either case you will get a product of minus 1, m minus 1s added together will give you minus m divided by m will give you minus 1. So, we have S dot S equal to 1, S dot T is equal to 0, S dot not of T is equal to 0, S dot not of S equal to minus 1. So, these are the nice properties we have if we have orthogonal codes. So, consider the following codes. Suppose these U, R, S and T, these are 4 different stations. So, we I mean for example, I mean here a simple example has been shown using only 8 chips. You note that say between U and R, okay, in one position they are same, this position they are same, 2 they are different, 3 third position in I mean this 5th position they are same. So, that is the number 3 position in which they are the same, and then there is a number 4 position which is the 7th position where they are the same. So, in 4 positions they are the same, and 4 positions namely the 3rd position, 4th position, 6th position and 8th position. So, in 4 positions they are different. So, the number of positions in which they are the same is the same as the number of positions in which they are different. So, we know that if we instead of 0 we have a minus 1 and 1 is 1, we do all those. So, these codes will come out to be orthogonal. Similarly, you will see that U, R, S, T they are all orthogonal to each other. So, their above codes are all orthogonal under the operation defined. Note that S dot T plus R is S dot T plus S dot R, which means that under normal addition, this if you take this as a normal addition. So, this dot product is going to distribute. Thus, under the assumption of linear addition of signals, S dot sigma of Ci is equal to S if and only if S is in Ci. That means, suppose there are a number of channels which are transmitting. In that case, if you see, so there we have already assumed linear addition of signal strengths. So, this is nothing but sum of the signal strength like T, R, U etc. they have been all added up. Now, S dot will distribute over this summation. So, we have S dot T and S dot R etc. Now, if S happens to be in this set Ci, then that S dot S will come out as 1. So, it should be 1 if and only if S is in Ci, otherwise it will come out as 0. Assume during any bit time U, R, S and T transmit 1, 0, 1 and nothing. That means, U is trying to transmit a 1, R is trying to transmit a 0, S is trying to transmit a 1 and T is not transmitting at all. If you use the codes shown in the previous slide over here, and then if you do the calculation, this will come out to be like this, that C, that the signal strength as we see it will come out as minus 1, plus 1, minus 3, plus 3, minus 1, minus 1, minus 1, plus 1. So, these are the 8 signal levels that we get. Now, if we do that C dot u, we will get a plus 1, that means C dot is trying to send a 1, C dot r will be minus 1, that means r is trying to send a 0, C dot s would be plus 1, that means s is trying to send a 1, and C dot t would be 0, that means C is not sending anything at all. If you remember that 1 0 1 dash, that means S R T, S R U and T, they are transmitting in this fashion. Okay. One implicit assumption in the above is that all stations are synchronized and transmit with the same power. In practice, perfect synchrony is difficult to achieve, resulting in the use of longer chip sequences and lower channel capacity. Secondly, to tackle the problem of power, each mobile transmits to the base station at the inverse of the received power. So, these are two things which are this thing. So, there are practical limitations, although this looks very nice. What happens is that there are practical limitations, and the theoretical maximum that we could achieve, we get less than that, but even then this is an elegant system. Now, we will look at some MAC protocols, two of them, two small ones we will discuss in this lecture, and then in the next lecture we are going to take two of the more involved ones, taking turns MAC protocol. Okay, remember that we had channel partitioning MAC protocols and random access MAC protocols and taking turns protocol. Okay. So, taking turns, what it tries to do is that it sort of allocates the turns, and we will see how. Okay. One could be through polling from by a master node, which is some kind of a centralized system. So, there is a polling of a overhead, latency, single point of failure, etc. So, we are not going to discuss this, at least not at this point of time. We are going to focus on this in this lecture and the next, which is token passing. Control token passed from one node to the next sequentially, there is a token message, concerns token overhead, latency, single point, etc. These are there. So, we will see some systems based on tokens now, which are sort of taking MAC using taking turns, all right. And the first example we are going to talk about is the token bus. So, they are even now they may be used, mainly used by assembly line factory. Okay. Assembly line factory, and it is used in factories for the main reason is that the other kind of system, which is the contention based, there is some randomness in the way communication can happen, and there may not be any hard and fast guarantee which people in process control and factories, etc., may not like. So, they may use this token bus, which has got the IEEE number 802.4. So, topology is just like a common bus and principle is like a token ring. So, there may be a okay, we will come to that. So, token is passed from high to low number of stations. Now, what is a token? Token is some kind of a bit pattern or some kind of bit pattern which is passed from high to low number of stations. Station with token will transmit. It is difficult to add and remove stations in this particular case. So, IEEE 802.4 determines the logical ring of the physical bus by the numeric value of the addresses, and MAC or LLC data unit provides the utility for the lowest address to handle the token to the highest address. Otherwise, the higher address gives the token to the lower address, that one goes. So, the predecessor gives the token to the successor, then the successor gives the token to the next successor, and so on all the way down the chain, and then there is some protocol for sending from the lowest one to the highest one in one go. Then the token is passed from a predecessor station to the successor station. So, this is sort of taking turns kind of thing, all right. The token is passed from stations to station in a descending numerical order of station address. When a station hears a token frame, that means it gets a token frame addressed to itself, it may transmit data frames. That means, when it gets the token which is addressed to itself, which has been sent by the node which is just higher numbered, which is just its predecessor. So, that is sending the token address to the next station. So, at that point of time it may transmit its data frame. When a station has completed transmitting data frames, it passes the token to the next station in the logical ring. So, if all of them are trying to transmit, they will sort of form a nice queue and then they will come back in a very regular fashion. That is the worst case. Of course, at some particular point of time node may not have anything to communicate. In that case, it will simply pass on the token to the next lower address, next lower MAC address. By the way, I have used the term MAC address earlier also. MAC is for medium access control, for that we require some kind of address. So, this MAC address. So, the a particular node, if it has nothing to transmit, it will give the control or the token to the next lower MAC address, and then the next lower MAC address will work. If it has something to transmit, it will transmit. So, you have some kind of worst case scenario in which that by the after this time, if all of them, what is the worst case? The worst case is then when everybody wants to transmit. So, that will take some time, but there is a bound to that time, and after that time your turn will come back again. So, there is a bound to the worst case performance in this token bus, but of course, this is not very efficient, not very fast. So, it may be getting sort of replaced now, but even in some factories this is still there. Now, we are going to talk about another technology named DQDB, okay, which was once proposed. It also had a name SMDA. So, it was once it was proposed as a solution for metro networks, and that means for metro networking DQDB was suggested and some were implemented, but now again DQDB is once again going out. It has a similar kind of principle, only thing is that instead of a single bus we now have two buses. So, let us look at DQDB very quickly. DQDB is 802.6. So, it is for a metropolitan area network spanning maybe 50 to 100 kilometers and operating at 34 to 45, even 155 Mbps speed was talked about at one point of time. This did not work out quite well later on, but anyway that is a different story. Originally designed like FDDI, we will be talking about FDDI in the next lecture for connecting LANs. Expanded to service packet switching at 2 Mbps and isochronous services. Isochronous means nearly synchronous. Features fixed length packets like 53 bytes long, and we will see ATM later which have sort of inherited this from this DQDB. So, later on. So, we will see ATM is still a strong technology even today. Empty cells are generated by the head end. So, there are two buses as I mentioned, and then at the end of the bus there are these head ends which generate a stream of empty cells. The stream of cells move in opposite direction in the two buses and finally fall off the other end. So, to transmit to a destination, the node has to know which bus to use. That means, whether it is to your left or right or up and down as is the case, I mean how, depending on how you look at it. So, it has to know that which bus to use for that particular this thing. So, this information every node must be having. It sets a request bit in some cell which is going in the opposite direction. So, this is for telling, suppose the node to which it wants to communicate is down, if I call it downstream in say towards the left, then it tells all the other nodes towards the right that it wants to communicate to this node on the left. It defers to downstream requests, counting such requests as they pass by. Nodes are not greedy. So, this is the heart of the protocol. Actually what it does is that, because otherwise what would happen is that if you simply get an empty cell and want to put in your data, then those nodes which are towards the end, they are sort of favored in a I mean it is not a fair system any longer, but then this scheme, if you think about it, will queue them up, queue the request in a first come first served manner, and then that is how that is why you sort of put in your request to the other side, so that those nodes on the other side would know that he is going to send something. So, to transmit to a destination, the node has to know which bus to use, etc. So, the nodes are not greedy. Its primary importance today is its close affinity to ATM and the consequential association with SONET and SDH, for which we shall see ATMs provides the approved switching fabric. Thank you. So, in the next lecture we are going to discuss two more token based protocols, namely token ring which was more common than this token bus or DQDB and FDDI. Thank you. Good day. In the last lecture we talked about various multiple access schemes, and one of this set of schemes in token bus and DQDB etc. were using tokens. Okay. Now we will use the we will see two other variants of it, namely token ring and FDDI. So we are going to talk about token based MAC, and specifically so there are some kind of round robin MACs, that means the chance to transmit comes to each of the station in a round robin fashion. This can be done, as I mentioned earlier, through polling or token passing. Here we will be specifically talking about token passing. So the first system that we will talk about is the token ring. All right. So as the name itself suggests that it is a ring topology, that it is a ring topology, and a token ring MAC works with a special pattern or token which is 3 bytes long. So 3 byte words of bits called token, which moves from one computer to the next. Priority indicators are placed within the token. How the priority indicators are used we will see later. So data rate may be 4, 16 or 100 Mbps, medium may be UTP, STP or fiber. Signaling is usually differential Manchester. We mentioned this earlier, what is differential Manchester, that how you represent your zeros and ones by electrical signals or optical signals as the case may be. And the maximum frame size would be about this 4550 bytes or right up to 18.2 kilobytes. Now let us talk about the type of network stations which may be connected to an FDDI ring. One is a dual attached station which is connected to both the rings. That means it is a station which is connected to both the rings, that is why it is called dual attached. Then we have dual attached concentrator DAC, which is connected to both rings and provides connection for additional stations and concentrators. It is actually the root of a tree. This is where the tree comes from. I have a picture. So we have this. So this is the picture of an FDDI concentrator. So you can see that this is the main part of the concentrator, and the two rings are there, the counter rotating. This is the primary ring and this is the secondary ring. So the primary ring is coming like this from A to B, and the secondary ring is going like this. It has some additional ports from which other stations may hang.